Hello everyone, this is lecture 19 of PTRE 465531, Petroleum Reservoir Geomechanics. This is the first lecture since the midterm. I cannot discuss the midterm because I know there is a couple that are still haven't taken it yet. And yeah, I mean, there were some incidents recorded on PTRE. They are going first to the administrators and then to me. I mean, generally those incidents are gonna be handled by the administrators if there is black and white. If it's a black and white incident, which is where most of them are. If there is a gray area, they will come to me. But I'm the one who comes second, so it won't go to me, it will go to the administrators. So I know there were some issues, nothing that major. There was a major one in the other class, I think. Somebody disconnected intentionally before the end of the session, and there were consequences. Anyway, so today we should finish module 2 and proceed, if we have time, with starting module 3. If we do that, I will put this lecture on the module 3 folder. If not, it's gonna be still on the module 2. Bearing in mind that the two reviews ahead of the exam were in the separate folder, yellow colored. I will be wrapping up this module talking about thermal effects, which we started talking about in lecture 17 actually. And it's pretty simple for Cartesian coordinates and cylindrical coordinates that we're gonna see later. We'll do this, wrap it up, and then move on to talk about failure. And this is stuff that we already talked about failure in module 1, kind of, mode 1 failure. In module 3, we're gonna talk about mode 2 and mode 3 failure as well. And then you have an exam sometime in the middle of November. And the second exam is gonna be mostly about shear failure. It's gonna have both kinds of failure in the exam, but generally the middle of it is gonna be shear failure, if I'm not mistaken. Or if I'm not mistaken, as to where I expect to be by the time of the exam. I don't think we'll need to postpone that. If it's needed, we can, but we are very good with the material. We're moving quite fast. There are some things I want to add for module 3. Also, there will be a homework between now and the next exam. I don't think there is time for a second homework in between, but there is at least 2 more homeworks left. So there will be definitely one between now and exam 2. And then there might be 2 or 1, depending on how fast we progress. And then there is another homework 4 or 5, depending on what happens between now and the exam. That will be after. Wellbore stability stuff. And then we are done with the class. And you guys will be ready for the next class, which will be well completions and advanced simulation techniques. A more applied version of these principles, actually. You'll see a lot of stuff there that you will see in this class. But it's more applied class. It's a more hands-on sort of class. And there is a term paper, 25% or 20% of the grade or something there. So it's the end of the 4 class series that you take with me. So generally by that time, the students are pretty like very, very well, they have a very good grasp on the topics and the principles that we are talking about. Okay, so the exam was captured all the way to what was slide 40. That doesn't mean that we finished. Oh, it was slide 40. So the exam 2 will start from slide 41 and onwards, the material of that will be on the exam. So we start from anisotropy onwards for module for exam 2, but there is time until then. If you didn't do well in this exam, don't. It's not the end. It's not a good thing, but it's not the end of the world. Like things can be turned over pretty easily at this stage. The important thing is not to have done terrible. Like the old saying, they say succeed very loudly but fail gracefully. You know, it's like don't give up in the middle of the exam because it looks hard and then get a terrible grade. Because if the next exam is easy, you would have been saying, "Hey, I wish I had done a little bit better on the exam 1, even if it was hard." So it would have been. You never know where the difference is. Somebody said once. You know, when you go for a race and you qualify, and then you start the race, how you qualify. Sometimes it's not about qualifying first. It's qualifying third. It's qualifying fifth. Qualifying sixth. It's gonna put you there, like in the sort of, how do you call it, the striking distance, to maybe do well in the race. You know, well. When I go for go-kart racing, I used to be in a state championship. It was, I knew I had to qualify well. My race was I was better on the race than on qualifying. So I was focusing on qualifying as best as I could. So I have a good chance in the race. Good days. Anyway. I thought about driving to Iowa 8 hours last weekend to do the race of October. The race is on the first Sunday of every month. And I thought if I drive to Iowa 8 hours and then 8 hours back, I could be back on North Dakota like by noon and be here for the class. But then it was like, it was exam week. So I was like, let's not risk it. Generally I drive to Colorado in the summer and I make it a road trip and I try to arrange such that I'm there at the right time so I can do the race in that Sunday and then carry on my road trip or something. Hopefully do the rest of the road trip with a trophy on the shotgun seat, you know? Anyway, so we were talking about thermoelasticity. We finished talking about poroelasticity in last time. And we moved to thermoelasticity, which you understand that's basically elasticity, linear elasticity with some thermal effects. And we did talk that temperature can cause elongation and shrinkage, temperature difference to be exact. Elongation, shrinkage, and that can bring like, you know, it's deformation. Deformation brings stresses and vice versa. And we said if you have a crack on your windshield and you live in a place like North Dakota, where it gets very cold in the winter and pretty hot in the summer, you may want to fix that crack before the temperature changes, because even in the winter, if you have an underground parking space, you will the underground parking spaces are generally at 65 degrees Fahrenheit. Outside is negative. So there is a big difference in temperature. So shrinkage and elongation makes the crack propagate. And it's basically becoming bigger and bigger. The glass actually behaves very well, very similar to the rocks. In fact, glass is made out of sand, right? So it does behave a lot like a rock. And those cracks you get on windshield are basically tensile failures. Maybe they didn't start as a tensile failure, but the way they propagate, it's very, very similar to the hydraulic fractures you try to do in the subsurface during stimulation treatments, when you do fracking, basically. A lot of people have experimented before moving into, for my master's, I did experiments on transparent gelatin. Before that, we did consider with my advisor at the time glass. But the thing with glass, we have to have a protective cover of the whole structure, and the cover had to be transparent too, so you can take a video of the fracture forming, and it was not easy. It was expensive stuff. So it was easier to go with gelatin. Anyway, so we have this equation that basically dictates the thermal dilation coefficient. It tells us how long the material will elongate in one direction because of due to a temperature difference. And it's something given in the units is in per degree Celsius or per degree Fahrenheit. You should be able to convert this from Celsius to Fahrenheit. Okay, and bear in mind that this just has to do is delta T. Okay, it's a magnitude. It's a difference in magnitude thing. So 1 degree in Fahrenheit is about 9 over 5 degrees Celsius. So shouldn't be that hard. Thermal effects are very, very important. Yeah, temperature drop causes shrinkage, temperature increase causes dilation, but what if you have a confinement? If you don't let the system dilate, you basically create stresses because the system wants to dilate, but the continuum wants to dilate, but you don't let it. You don't let it, and that induces stresses. Applying this impact of the thermoelasticity onto the Voigt notation, we get these equations, which basically we take the normal stresses, well, in this case, it's normal effective stresses, and we add plus 3 times the bulk modulus times alpha T, the thermal dilation coefficient, times delta T. Okay, all those terms are added at the end of every equation for the normal stresses, not for the shear stresses. Shear stresses stay the same. So remember, just like pore elasticity, thermal effects only affect the normal stresses, just like pore pressure too. Yeah, it can impact whether you get fracture gradients like tensile fractures when we do fracturing of a rock. The change in temperature can cause big can make a difference between having a fracture or not, and I will give an example later. And same thing for shear failures like earthquakes. It can make a difference on whether you will have an earthquake or not. And one example is that in Alaska, back, I want to say, was it 80s, was it 90s, was it early 2000s? There was a pipeline bringing water for water flooding in Alaska, in Prudhoe Bay. And they had sweep efficiency issues. And if you take reservoir simulation or reservoir engineering in general, you should know what sweep efficiency is. Like you are injecting a fluid, it doesn't go where you expect it to go. There is some paths of low resistance in the reservoir where it basically it steals your water. It doesn't go where you want it to go. And when you have sweep efficiency, everybody thinks about fractures. Okay, maybe I have a fracture, maybe I have a fault that is stealing my water that I'm injecting to move the oil to my producer wells. And anyway, they asked the operators, they said, hey, no, we're injecting below the fracture gradient. Are you? Yes, we are injecting below the fracture gradient, sir. No, we are not exceeding it, and we have a safety margin for that. Anyway, so somebody did a study, and I believe the study was conducted by University of Texas or somebody I knew from University of Texas. And what they decided that was happening, based on the evidence they have seen, was that because the water was piped to the injector wells with a pipeline, the cold temperature in Alaska was making the water that we injected very cold. And the interaction of the cold water with the rock, it made the fracture pressure of the rock, the fracture gradient, to be reduced. So even if you thought that you were not fracturing the well, you were fracturing it because the fracture gradient or the fracture pressure was lower than what you thought it was, what they thought it was, because it was you're injecting something cold. Then if they were injecting hot water, you will make it harder to fracture. So these are important things. Sometimes temperature can be important. One of my graduate students, Nasim, he investigates fracture initiation from the point where it initiates, like the intersection between the wellbore and the perforation. And he has a model that is called TPHM, thermo-poro-hydromechanical. Thermo means thermal effects, poro means poroelastic effects, hydro means fluid effects, mechanical means stresses. And he did find that thermal effects are actually could be important. They are not insignificant. They are not crazily significant, but they can be important. I think that's the right conclusion from his work. One of the conclusions from his work. Soon in peer review. Yeah, so thermal effects are not to be ignored many times. What I was gonna say about that, yeah, it's not like the well is gonna raise a flag and say, hey, I'm fracked, stop pumping, you know? I mean, you really inject, you keep injecting, you created a fracture, you don't know. Many times in drilling, when I was working for drilling, in a drilling rig, we were creating fractures and we didn't know that. And then we were having low circulation and we were wondering, hey, why are we losing circulation when we're in the shale, you know, which has low permeability? And the answer was that we created a fracture, and then we remove pressure, it closed down, and then we increase pressure, it opens up and steals your mud, and then close down when you are lowering the pressure, and then it opens up, closes down, and it goes on like this. By the way, I want you to be very familiar, and you should be familiar with the difference between fracture pressure and fracture gradient. Okay, gradient is the fracture pressure in psi per foot divided by the depth. Fracture pressure is an absolute value of psi, let's say. And I think we have an example problem to worry about. Derive an expression of the thermal swelling stress along the vertical z direction for a homogeneous, isotropic, linearly elastic solid, which is heated up but not allowed to dilate in the vertical direction. Okay. So this is the statement. The first paragraph is the statement of the problem. So it tells me I have a isotropic, homogeneous, linearly elastic solid. So that tells me I can use the Voigt's notation. But what do I know? It's heated up, but it's not allowed to dilate in the vertical direction. So it's telling me that epsilon zz, the strain in the vertical direction is 0. So I am not allowed to dilate in the vertical direction. But it's also telling me that I have a thermal swelling stress along the vertical direction. So I have no stress in the x and the y direction. So sigma xx and sigma yy are 0. And it's also isotropic. So whatever strain I have in the x direction, I also have in the y direction. So, okay, let's go back to this Voigt's notation. And remember, we said Voigt is a whole matrix equation, but these equations here are what result from the Voigt notation, right? If I take the matrix and I multiply them, I make them six equations with the thermal effects. This is what I'm gonna end up with. Okay, so what I'm told is that this is 0 and this is 0. I'm also told that this is 0. And I'm also told that epsilon xx equals epsilon yy. So I can convert those into one unknown, right? So I can make this epsilon xx. This is 0. I can make this epsilon xx. This is 0. And I can make this epsilon xx. The other one is 0. Okay, so now I have, excuse me, I have basically 3 equations, but if I look at them well, the first 2 are the same, okay? Because I said epsilon xx equal to epsilon yy, and epsilon zz 0, so it doesn't affect any of them. Those 2 are the same. So I have basically one equation and another. The third one becomes the second equation. So I have 2 equations and 2 unknowns. What are my unknowns? My unknowns are epsilon xx and sigma zz. So I have 2 unknowns. And I have 2 equations and 2 unknowns. And I'm trying to solve them so that I can calculate an expression for the thermal effects, basically. So I have those two equations that I wrote down. The first two equations lead to this. Can I write here? Okay. And the second equation leads to this. Now, how about I take the first equation and it's basically simultaneous equations, okay? I can, and you have learned in school how to deal with those. Let me deal with one way. I solve the first one for epsilon xx, and I plug it into the second one. So I will have epsilon xx lambda plus 2m minus lambda equals to 3k alpha t delta t. If I'm not wrong, and I am, okay, this and this. I was trying to do it the other way. And then I have here epsilon xx 2 lambda plus m is equal to minus 3k delta t. And then I will have epsilon xx equal to minus 3k delta t divided by 2L plus M, unless I'm very much mistaken. Now, I don't know if I have space. Will it let me write here? Okay, it does. Sometimes it doesn't. In the other class, oh my God, it doesn't let me write when I'm low on the slide, and it's super frustrating, especially when the time is running out and you are trying to get something for the students. But anyway, you have 2 lambda minus 3k alpha t delta t divided by 2 lambda plus me plus 3k alpha t delta t. Okay. These two cancels out. And then you have you can basically solve going onwards. And you are gonna end up to something like this. If you start, if you keep on trying to solve this, you are gonna end up to something like this. And you can see how this equation impacts. Oops, so you get rid of the lambdas, and you basically get only m, k, and then the rest are basically the thermostat, alpha t and delta t. And you can solve it basically for the plane stress assumption. You have stress only in one direction. You have strain in two directions, and you apply stress basically. Yeah, you have stress in one direction, plane on strain on the other two, but in this case they are equal strain. So you have isotropic as well. It's isotropic plane stress problem. And yeah, I think I did it. Let me see if I can. Will it let me? If I can. Yeah, but basically, yeah, you solve for epsilon xx and you plug it into the second one. and then you basically rearrange stuff, and you should be able to um, eliminate lambda, and you're gonna be stuck only with mu and k, and then you can solve this. And remember, oh yeah, remember something. This is one version of the equations. You can have it, you have two unknowns, right? M and K. Lame's second parameter and bulk modulus. What if you have, I'm pretty sure, and you can rearrange this equation, rewrite this equation, the same thing with Young modulus and Poisson's ratio, or Young modulus and M, or Young modulus and K, or Poisson ratio and K. You only need two unknowns to get basically what is in this parenthesis. You can convert it to other stuff too, or you can use the shear modulus. They are all interrelated. Now, I don't want you to do that, but I want you to know how to go from, I want you to know how we went from basically these 6 equations to these 2, and then to this. So this problem was basically a hypothetical plane stress problem. Have a material, it's a continuum. It's in this sort of bucket, let's call it. I don't know, maybe gelatin, and it's in a bucket, and the bucket has much stiffer walls than the material itself, so it will never flex. And I apply heat, but the heat, I apply heat, you heat, look at how easy it is now that it's letting me right at the bottom of the slide. The heat is causing a dilation. Oh, sorry, I was wrong. 1 second, let me just read the problem again. Yeah, sorry, it was the opposite. I should have drawn, this is the plane straight. Sorry about that. 1 second, let me clean this up. Sorry, forget about what I drew. Maybe it's better to draw it as, yeah, I forgot it doesn't let it. I drew the plane straight, not the, okay. It's a material like this. These are the plates that are not allowed to flex. And the material is in the middle. Okay. I'm heating it up, but it's not allowed to expand in the Z direction. This is the Z direction. This is the X, and this is, and this is Y, I guess. Forget about it. Let's do it. It's a 2D, so this is the Z direction, okay? I'm not allowed, I heat it up. I'm forcing epsilon ZZ to be equal to 0, okay? I'm not letting the material expand. And because of that, I have a sigma ZZ, obviously. Now, I am letting the material expand, though, in this direction. And also, which is X. and then also in this direction, out of the plane of the screen, which is the Y direction. It's like coming towards me, like it's coming out of the screen of your screen, let's say. So I have epsilon xx. I have epsilon yy. Oh, why did I write it like it? And I have epsilon yy, and they are equal because it's an isotropy. So I have one stress and two strains, but really one strain and one stress. And I create two equations from Voigt's notation. I write them, I solve them simultaneously. I rearrange one, plug it into another, solve them, and go home. And I'm sorry I didn't draw it correctly the first time. I was thinking of a plane strain problem, but this is a plane stress. Generally speaking, plane strain is more applicable to what petroleum engineers are looking into. For reasons that we have discussed earlier in this module, actually. Remember when I drew the big hemisphere for the vertical overburden stress and those stuff? That was a pretty representative problem. And that concludes module 2. What did we do? We introduced solid continuum mechanics, although you have already seen them in solid mechanics. We talked about stress equilibria, kinematic, and constitutive relationships. Stress equilibria was Cauchy stuff. Sigma phi in all directions equal to 0. Kinematic, we related strain to displacement. And then constitutive relationships, we related stress to strain. Very, very important. We talk about the 6 moduli of linear elasticity and their interrelationships. Yes, it was a tough module, but now you are very familiar with linear elasticity having 6 moduli, and you need to know only 2 to get the other 4. So it's a very, very easy model, very, very simple model. It's a linear model. Not many things in life are linear, but linear elasticity is very, very easy to work with, relatively speaking. We talk about anisotropy and heterogeneity, and we introduce 2 models of anisotropy, very, very simple models. Vertical transverse isotropy, which is an anisotropic model. So VTI, vertical transverse isotropy, is a model of anisotropy, and an orthorhombic anisotropy, which is different x, different y, different z. One more or 2 more. We talk about poroelasticity and thermoplasticity. Well, in fact, we did talk about linear poroelasticity and linear thermoplasticity, to be exact. These 2 can become much, much more complicated than what we have seen in this class. And if there is ever a class in advanced geomechanics, which probably I will have to teach in this department, we are going to be getting more deeper in this stuff. They can get very, very mathematical to the point it can scare the horses from here to California. It can get very, very complicated, okay? Poroplasticity, elastoplasticity, I mean, it can be very, very mathematical heavy. I mean, I have seen some of those books. Oh my God, like the derivations were crazy. And that's it about module 2. We finally finish it. And I know it was a hard one. I promise the next one is gonna be better. It's more applied. Students generally like module 3 more than module 2. And out of my 4 classes, this module is the one that the students hate the most. They're already always happy when they are done with it. The next one is gonna be more, and we're not gonna start it in this lecture, but we're gonna see failure in more detail. We have already seen tensile failure, but we are not done with it. Mode 1. We are gonna see shear failure as well now, and in the next one. Nice. We're gonna see some pretty fundamental stuff. And you may have seen some of those in your solid mechanics classes already. Anyway, I'm a little bit sick, so I will call it for today. We will carry on Wednesday with module 3. So I guess I will put this in the module 2 folder, this video. And on Wednesday, we start the module 3 fresh. Thank you very much. Have a nice rest of your day.